Here we go. Casual, casual conversational cartoon curriculum. Very concise and relatively correct. As soon as possible, as simple as possible. A&P, Chapter 5, fifth installment right here. We talked about how connective tissues are built, what they're built of. Now let's go after the names of these things. How are they classified? As you learned in lab, connective tissue tends to be classified as fibrous, cartilaginous, osseous, or vascular. Now, for each one of these things, I have the letter F next to it to represent the amount of fiber in it or the amount of visible fiber in it. They all have fiber inside of them. It's just a matter of, is it visible? Is it obvious? Is there some kind of trick to it all? For a fibrous connective tissue, they tend to fall into two categories. They're loose connective and dense connective. Under loose connective, you have fibers that are shaped and sort of pointing out in all possible directions. They take up space dramatically. And that's the case with areolar tissue. In fact, the name areolar comes from the word area. You tend to find areolar tissue in places of the body where something else isn't. So it's like spider webs in a house. You find spider webs in a house where something else isn't moving through. So areolar tissue, very, very abundant throughout the body. It tends to put a fuzzy surface to things that are connected to each other, such as arteries and veins, to other structures of the body. Reticular loose connective tissue. This stuff right here, again, is more branching, as you expect to find, say, in lymph nodes, liver, spleen, where you're creating a space for other cells to perch inside of. And then there's adipose tissue, or so-called fat cells. Now, these things have the ability to invade areolar tissue and take it over. So adipose tissue is usually areolar tissue that has been taken over by fat cells that moved in, expanded themselves, duplicated themselves, and took all the fibers of the areolar tissue and squished them between the expanding adipose cells, adipocytes. Dense fibrous connective tissue, they tend to be irregular, regular, and elastic. We'll focus on these two right here. Dense irregular connective tissue tends to have the same fibers, that were found in areolar, but now they're woven tightly together. Looks sort of like ramen noodles in a block, or plywood, the appearance of plywood, one layer on another layer. These things tend to flatten out in one plane, and so therefore they make a kind of a fabric. And most of the capsules of the organs in your body are made of dense irregular connective tissue. The dermis of your skin, most of it is dense irregular connective tissue. Leather is just a commercial name for the dermis of an animal, and it's tough because it has dense irregular connective tissue. Dense regular connective tissue. On this one right here, well, areolar is they're going in all directions. Dense irregular, they're woven together in a pattern, but in dense regular, the fibers are all going in the same general direction. So you tend to find these things in places where there's a pull in one direction. So that would be tendons and ligaments. Cartilaginous tissue. Oh, and the fibers in these are quite obvious. Cartilaginous tissue. Okay, this stuff has fibers in it. Sometimes it's not visible, and sometimes it's very visible. Here are three examples. We'll focus on the top and the bottom one. And hyaline cartilage. The word hyaline does mean glassy, and you remember from lab that when you look at hyaline cartilage, it kind of looks like plastic, and it's got bubbles inside of it. Well, those bubble-like structures inside are chondrocytes, which are trapped inside spaces called lacuna. And around them is the matrix, and the matrix usually has a clear appearance to it. You don't see the fibers inside of it. Now, in fibrocartilage, you've got lacuna, you've got cells inside, and then you have a matrix that has obvious threads inside. This tends to be in areas where there's a lot more stress and pressure than this right here. So these lacuna and chondrocytes tend to be rounded and bubble-like. These things tend to be flattened out, sort of slinky looking. Osseous tissue is bone tissue, and there are fibers inside. It's just that they're surrounded by salt crystals, calcium salt crystals, and you can't see the individual fibers. Osseous tissue comes in two general forms: compact, dense bone, or so-called cortical bone, and then spongy bone. This is the stuff that makes it the outside of a soup bone, and this is that stuff on the inside that looks like it has a lot of spaces inside. It's spongy by its appearance, not by its texture, its touch. It's solid material. It's just got a lot of gaps in it. And then, of course, vascular is the fancy name for blood. And yes, there are fibers inside blood, but they're dissolved fibers. These fibers do come out, however, when you form a blood clot. So the fibrous material is there, it just hasn't formed threads until it's activated. Okay, something else over here that's kind of unique to connective tissue is these types of muscles called gag muscles, materials called gag molecules. And GAG stands for glycoaminoglycan. In general, what it is a long chain that has nitrogen components on the thing, and it tends to carry a negative charge on the outside edge. So it is a polysaccharide, long chain there, polysaccharides, the sugars attached to each other. It has amino acid groups, nitrogen groups attached to it, and it's surrounded by negative charges. These negative charges, by the way, have the ability to attract water. So this stuff right here tends to stick to water, or we can say water sticks to it. Now that's just a GAG molecule. If you take GAG molecules and you attach them to a central protein molecule, then you've created something called a proteoglycan. It's the protein and GAG molecules. The structure right here sort of kind of looks like a brush with bristles on it. And the solid core is the protein, and the bristle-like structures are the GAG molecules. What's cute about this is, if there isn't a lot of water attached to the GAG molecules, this whole thing is kind of floppy, sort of deflated, and so it's soupy. However, if water molecules come in here and surround the GAG molecules, they kind of fluff up, it becomes a little bit more solid, and you form a gel. So this material, proteoglycan, is a common component of any gel-like material, as in cartilage and such. Examples of GAG molecules is chondroitin and hyaluronic acid, two things that you've heard about when it comes down to makeup, trying to fluff up your skin to make you look young again, or something that's supposed to fluff up your cartilage inside your joints and make them act young again. Over here, just an analogy again, things we've talked about before. Proteoglycans, just talked about those things. They form gels in your body. But then there's something from chapter 4 called glycoproteins, and these things tend to form glues inside your body, like that glycocalyx. Both of these things can be found inside of cartilage. Over here, let's finish this thing off by talking about the fibrous jungle. Just an analogy that areolar tissue is very much like a jungle. A jungle has trees and vines, sort of creating the character of the space. Well, areolar tissue has fibers that stretch all over the place and create the character of the space. Jungles have pathways along which some things can move. Well, inside areolar tissue, there's ground substance, semi-fluid material that things can move through. And in jungles, there's creatures out there, some seen, some unseen, some that live there, some that are just passing through. And inside areolar tissue, there are residing and wandering cells. And these things could just live there, and they're attached there, or they could be just wandering through. Here are some quick examples of some residing cells that may be found in areolar tissue. Fibroblasts. Fibroblasts, of course, are responsible for creating the fibers that create the jungle web-like appearance right there. Now, these fibroblasts secrete chemicals. The chemicals polymerize and form the threads. And so therefore, it's not pulling a thread out of itself, it's producing chemicals. The chemicals self-assemble. The analogy right here is silly string in a can. When you shake a can of silly string, party string, it's a fluid. But when you push that nozzle and those chemicals hit the air, they polymerize and form the string. Adipocytes. Remember, adipocytes move into areolar tissue. They're small. They start forming an inclusion, an oil droplet right here. As they get bigger, they push all the fibers to the side. And we like to make the analogy that oil in an adipocyte is like a bank CD. It is stored energy. It's easy to put it in, but it's kind of difficult to get the stuff out. So, and they're very, very resilient. They're very, very stable. Then there's mesenchymal cells, and mesenchymal cells are those kind of stem cells that don't know what they want to be when they grow up. But according to changes in the environment around them, they will select a path. And so therefore, according to the need of the environment, they become either a fibroblast, chondroblast, osteoblast, or maybe a hemocytoblast. We like to make the analogy that a mesenchymal cell is like an undetermined major in college. This person is training to be able to go in all kinds of different directions. They just haven't figured out which specific direction yet. And then we talk about something called fixed macrophages. Now, macrophages are a type of a white blood cell, and these things are ferocious killers. We can make the analogy here, there's like the Tasmanian devil in those Looney Tune cartoons, or they're like a junkyard dog. These white blood cells go after anything they do not recognize. So they're out there patrolling, looking for any foreign object or any abnormal object to destroy it and keep the area clean. Those are residing cells. Now, as far as wandering cells, well, you have free macrophages. These are like these junkyard dogs that are off the leash. They can wander around and find things. Here, the thing has to get close to the macrophage. Here, the macrophage goes out there and tries to find it. Again, it's a major component of your immune system. But then there are also plasma cells, and plasma cells have the ability to make antibodies. And the silly analogy right here is a plasma cell is sort of like an insecticide spray. It produces a chemical and fogs an area. It's the chemical that does the killing, not the cell. The cell doesn't go and fight something. It just creates the chemical, which then destroys something. Neutrophils, another type of white blood cell that's found wandering through this neighborhood. These are like foot soldiers of your body. They're found in large numbers, and they're very often the first cells to show up, white blood cells to show up when there's an infection. The good news is they come in first, they come in fast, they have a lot of cells show up, but unfortunately they don't have the best weapons around. But they do bide time for something else to come in, hopefully macrophage. Then there are also T cells that might be out there wandering around, and T cells are part of your immune system. These guys are like assassins in which they have one single target that they're looking for. They don't handle all problems. They just go after one single target. And so that kind of limits them in what they are capable of doing. And the last general character right here is called a mast cell. And the mast cell is a type of white blood cell that's part of your early alert security guard kind of a system. They don't necessarily attack something, but they do spread an alarm when something unusual happens. So they have granules inside their cytoplasm that contain a variety of chemicals, including histamine. And when they do bump into something that's wrong inside your body, such as a bacterium or a broken tissue or something like that, they dump the histamine into the interstitial fluid. And the histamine causes a wide variety of effects, including attracting other white blood cells to come in and handle the problem. Now, the general process right here is called inflammation. And with inflammation, we did say that there's 4 basic cardinal signs to it, and there is pain, edema, redness, and heat. Here's the quick story. When a wandering mast cell bumps into an odd material, it gets all excited because it's odd, and it dumps histamine into the neighborhood. The histamine and other chemicals can cause blood vessels in the region to vasodilate, get bigger. When they get bigger, more blood moves into the area, and so therefore there's more heat and there's more redness. It also causes the blood vessel to become more permeable so things can leave the blood and get into the interstitial spaces. That will allow fluid to leave the blood, get into the interstitial spaces, and that creates the edema. So increased blood flow meant increased redness and heat, and increased permeability means increased edema, and possibly an explanation for pain, because again, pain is one of the 4 cardinal signs. Pain because the cells are being stretched out of their normal position, and nerve fibers may be stretched out of shape, but also some of the chemicals actually enhance pain purposely to make you aware of something not being right. Again, the chemicals being released can attract more neutrophils to the area and more macrophages to the area. It's the neutrophils that show up first in large numbers, and they try to hold the line until macrophages show up later on, sometimes as late as 12 hours later, but they come in like the cavalry to save the day.